Okay, that was good. Lordy. Laracon, huh? Bunch of PHP programmers? Is that what I'm talking to here? How the mighty have fallen. So, tomorrow will be the longest lunar eclipse of this century so far. Of course, there's only 18 years in this century so far, so I'm not quite sure why that's significant, but it made me think that we should talk about the moon. There's a number of problems with the moon. Like, where did the moon come from? So when I was a kid, that was a very, very long time ago, 1960, let's say. When I was a kid, my science textbook showed where the moon came from. They said, well, there's several possibilities. One of the possibilities is that the moon was captured as some errant asteroid that came by. And another possibility was that the moon and the Earth formed together at the same time. But another possibility was that the moon kind of bubbled out of the Earth. And then, as I turned the page in the science textbook, there was a picture of the Earth centered on the Pacific Ocean with a picture of the moon superimposed upon the Pacific Ocean, and it fits. The moon fits right into the Pacific Ocean. And the caption was, the Pacific Ocean could be the crater out of which the moon bubbled. It's a very old science book. Where did the moon come from? How did we get this moon? There's a number of problems with the moon. Number one, it's in a circular orbit. Is it going to work again? Number one, it's in a circular orbit. You can't capture something into a circular orbit. If some errant asteroid comes by, it's going to wind up in some horrible elliptical orbit, not a circular orbit. So there's a problem with that. And in fact, the only way to get a circular orbit is some kind of co-creation event where the two bodies are so close to each other that their angular momentum couples, and the one is driven out by the other, and it circulates the orbit. So that's a problem. Now, you could solve that problem by saying, well, the Earth and Moon formed at the same time, but there's a problem with that. The problem with that is that the orbit of the Moon is not in line with the equator of the Earth. The equator of the Earth is tipped by, what is it, 23 degrees? Something like that? Okay. But the orbit of the moon is in the plane of the solar system. The angular momentum of the moon has more to do with the sun than it has to do with the Earth, which is very weird. That kind of argues against this co-creation idea. Another problem is that the moon is tidally locked to the Earth. You don't get a tidal lock unless the two bodies start in close and then the angular momentum couples them out. So the moon had to start in close, the angular momentum had to couple them out, but they could not have formed at the same time because they have different angular momentums. And then the last little bit of evidence, which the astronauts brought back in moon rocks, is that the moon and the Earth are made of almost identical material, down to the isotope ratios. The ratio of the isotopes of oxygen, for example, are almost identical with that of the Earth. Now, if you get a Mars rock, you'll see a different isotope ratio. So the moon and the Earth formed out of the same material, except for one thing. The Earth has a ton of iron and the moon has none. So they couldn't have formed out of the same material because the moon has no iron. Now, how do you resolve all of these issues? And the way they've resolved all these issues is to very cleverly come up with a catastrophe. Right? Apparently, a body roughly the size of Mars formed inside the orbit of the Earth at about the same time that the Earth formed, at about 60 degrees away, so at one of the Lagrange points, a gravitationally stable point. And eventually something upset that little body that's about the size of Mars, and it slowly slid over and slammed into the Earth, melting both bodies. The two iron cores go to the center of the Earth. These lightweight silicates all splash into a ring. The ring, about a century later, coalesces into the moon a few thousand miles away, and then they couple their angular momentums and drive the moon out and tidally lock the moon. It explains everything. Wouldn't it have been fun to watch that? No, well, enough said about that. Now, I'm supposed to give a talk here. I don't know if you can see my screen. It's a talk about architecture, I think. Do PHP programmers know anything about architecture? No? Okay, all right. I'm talking to the right crowd then. This is a talk I've given many, many times before in many different venues, and it's essentially the theme of the book that I wrote recently called Clean Architecture. It came about a long, long time ago. My son was writing a Ruby on Rails application. And he handed me the source code to it, and I was looking through the source code, and I saw something funny. See if I can bring that up here. Let's see. I think I do it this way. There's way too much technology here. I've got an iPad, and the iPad is talking to an HDMI port, and it's going over video signals all over the place. And it's just a miracle all this stuff works. Yeah? And it works, it's pretty reliable. Most of the time, pretty reliable. So nowadays, I do all my presentations on iPads. There we go. So this is what my son handed me. And I looked at it, and I said, yeah, that's a Rails app. You can identify it almost instantly just from the directory structure. You see the funny little directories in there, like the DB directory and the controllers directory and the models directory. All that stuff is a very typical kind of Rails directory structure. And I'd seen lots of Rails apps before, and I knew what Rails apps were, and this one didn't surprise me at all. And then all of a sudden, I scratched my head and I said, wait a minute. Why is it that the first thing I see when I look at that directory structure is a Rails app? I don't see what the application does. I see a Rails app. Why does the framework dominate? Why is the framework yelling at me from the midst of that directory structure? And I realized at that moment that something was wrong with that. Now, why didn't I realize this before? Well, does anybody remember 1999? You got a few people out here old enough to remember 1999. So 1999 was the pinnacle of the dot-com era. And then we all lost our jobs and our minds. Our particular industry is always in demand. How many programmers are there in the world, do you think? Not enough is the right answer, but how many are there? How many programmers are there in the world? It depends on if you count all the PHP programmers, and there's some debate about that. I usually say VBA programmers for that one, but I decided to give you guys a little plug. There have to be somewhere on the order of 100 million programmers in the world. Now, there's 8 billion people in the world, and 100 million, well, that's what, 1/80th? Is it possible that 1 out of 80 people, 1 out of every 80 people is a programmer of some kind? Is that possible? I think it is. All right, so let's presume for the moment that there's 100 million programmers in the world, because if there aren't now, there will be soon. How long ago did the first programmer write the first line of code to execute on an electronic computer? What year was that? That was 1946. 1946, Alan Turing wrote the first instructions to actually ever execute on an electronic computer. Some other people had written program-like things before that. But you and I would recognize the code that Alan Turing wrote in binary, in base 32, in 1946. That's one. And what's the year now? 2018? That's 70, am I doing that math right? Let's see, 58 plus 18, 76? 76 years. In 76 years, we've gone from 1 to 100 million. Now, you can do the math there. What kind of growth curve is that? Is that a linear growth curve? It's clearly not a linear growth curve, right? So it must be some kind of exponential growth curve. Okay, well, if it's an exponential growth curve, let's use the base of 2 and figure out what exponent of 2 gets us from 1 to 100 million. Okay, well, 2 to the what is 100 million? What is the log base 2 of 100 million? Okay, log base 2 of 1,000 is 10. Log base 2 of 1,000,000 is 20. Log base 2 of 128 is 27. Takes 27 doublings to get from 1 to 100 million. 27 doublings to get from 1 to 100 million. In 76 years, there have been 27 doublings. How many doublings per year? Or how many years per doubling? 2-ish? Does the number of programmers in the world double every 2-something years? It's not very fair, because in the first decade, the doubling rate was much higher. Alan Turing might have been the first electronic programmer, but a week later there were a dozen. So it was probably very high at first, and then it slowed down. So let's just say, for the sake of argument, that the number of programmers in the world doubles every 5 years. Is that realistic? Does that feel about right? Does the number of programmers double every 5 years? The number of programming opportunities double every 5 years? This is the kind of industry that you and I work in, right? Where the demand for programmers doubles at an insane rate. So in 1999, we had a little hiccup. Those are rare in our industry. Usually, if you're a programmer, you're going to have a job, a pretty good job, a well-paying job. And you will probably have that job for as long as you want it, because the demand continues and continues and does not abate. And we find all these interesting things to do with computers. How many computers are in this room? How many computers are on my body at the moment? And there's this one. Now, you know, an iPhone, how many computers are in this? There's a graphics processor and another processor and a Bluetooth processor and a GPS processor. There's probably 6 or 7, maybe 8, 9, 10. God knows how many. And then I've got this thing in my pocket, AirPods. And there's at least one processor in each one of the little AirPods. There's probably 1 or 2 processors in the body of the damn thing. Right? Got my car keys. There's at least one computer in there. I have on my body over a dozen computers, just sitting there running code, written by some 22-year-old at 3 in the morning. Right? Okay. How many computers are scattered in the walls of this room where you can't see them? Right? Funny little computers just hidden away in the walls. Like the speakers, right? The speakers have little computers in them, because nowadays you don't want to put a capacitor and an inductor to filter out 60-cycle hum. You want to put some little DSP in there that has code written in C to do fast Fourier transforms to notch out the 60-cycle hum. So all the little speakers in the room, they probably have little computers in them. How about the exit signs? Do the exit signs have computers in them? They have batteries. Because if the power goes out, you want the exit signs to still stay lit, and those batteries have to stay charged. And the way we charge batteries nowadays is to have a little digital signal processor trickle charging those batteries to keep the memory effect from compiling. So yeah, there's probably computers in those damned exit signs. If you think very carefully, you will come to the realization that every second of every day, you are in contact with some computer system. And not just you. Your grandmother is in contact with a computer system every waking moment of her life, because in our society, you can't do anything without interacting with a software system. You can't buy anything, you can't sell anything, you can't make a phone call, you can't start the microwave oven, you can't wash clothes or dishes, you can't drive your car. Oh God, your car. How much code is running in your car? How many lines of code, horrible, horrible code, are running in your car at the moment? And you get into that thing and you drive like, oh, it's going to be fine. You ever wonder, midnight, February 29th, leap year, if the guy did the math right, is the car going to actually work, or is it going to turn upside down? Our society depends on us, you and me, programmers. They don't quite get this yet. We don't quite get this yet. The level of dependence that our society has upon computer programming, and therefore computer programmers, is enormous, well beyond the stage of critical. Enormous. And our society does not quite understand, although they are getting that understanding, just how awful our industry is. They got a hint with the Volkswagen fiasco. Anybody remember that one? Interesting, right? Right? We're gonna sell the Volkswagens in California by cheating the device, the little testing mechanism. Now, you know what they did, right? They somehow detected that if you were on a test rig, then they could tune the engine to cut down the nitrous oxide emissions, right? But then in the real world, when you were out on the road, they just cranked those emissions right up because you get a lot more power that way. Can you imagine the discussion that occurred amongst the software developers when the management told them we got to find a way to deal with this testing problem, and the hardware guys have said they can't do it. The diesel engine just can't do it, but you software guys, you can solve this. And can you imagine a software dude sitting in a conference room going, okay, man, like how do we detect, we're on a test stand. Like, how do we do that? Because, like the wheels are turning, but the car's not moving. Like, we could look at the GPS. Right, if our GPS velocity is close to 0, then we would know. Who watched the testimony of the CEO of Volkswagen North America before Congress? How many of you saw that? And, Congress, some got congressmen, because they're all obnoxious assholes as congressmen, and they look at the guy and they say, all right, now how could you have let this happen? And the CEO of Volkswagen North America said, it was just some software developers who did it for whatever reason. That is a direct quote. And guess who got blamed? The CEO of Volkswagen North America pointed his scrawny little nail-bitten finger right at you and me. Deservedly so, because it was a couple, or maybe more than a couple, of software developers who wrote that code. And you can say, well, those software developers, they didn't know what they were writing. Yeah, right. If So in 1999, the world went upside down, both because of the dot-com thing and because of the web and the internet. And we all thought, everything has changed. Everything's different now. Right? The web has come, everything is different now, and the dot-com thing happened, everything is different now. And for, 15 years, we kind of coasted along with this, everything is different now. And then, maybe about 2012, 2013, it occurred to us that nothing at all had actually changed. That the web was not anything abnormal. The web was just a normal kind of request-response protocol that we've been dealing with for 40 years. Okay, slightly different format, but anybody out here work on 3270 green screens? Do we have any old gray hairs out here that wrote the hypertext that went out to the 3270 green screens and got the forms that came back from the 3270 green screens, worked just like a browser? Maybe not quite as impressive, but same idea. There's nothing new about any of that. Does anybody remember the emphasis we had in the mid-90s on design and architecture? It was the heyday of design and architecture. You had Ivar Jakobsen talking about it. You had Grady Booch. Who knows who Grady Booch is? Who's heard that name? Right? In 1995, I guarantee you every single software developer knew that name. Because how could you not? Grady Booch. Right? It's a great name. Right? Now it's gone. Nobody knows. Nobody's seen those books. Nobody's read those books. Who knows who Ivar Jakobsen is? How many of you have heard the name Ivar Jakobsen, right? In 1995, I was at a conference just like this one, and Ivar Jakobsen was about to release a book. The books were there at the conference. We all lined up because we wanted to get that book, Object-Oriented Software Engineering by Ivar Jakobsen. This was the heyday of design and architecture. We were all focused on design and architecture. Getting the design right, getting the architecture right was really important. And then the web came along and blew that stuff out of our brains and kept it out of our brains for 25 years. So my son hands me this source code, and I look at it, and at first I think, yeah, that's a Rails app. And then it occurs to me, wait a minute, where's the architecture? Where's the design? What the hell does this app do? And why is it that all I see is Rails? Is Rails really that important? Should Rails be dominating everything? Well, no, it shouldn't. Why? Because the web is an I/O device. The web, I'm going to say that again, is an I/O device. It's nothing else. It's just a way to get stuff out and get stuff in. The web is an I/O device. And do you know what we learned about I/O devices in the 1960s? In the 1960s, we learned the hard way that when you wrote code, you did not want your code to know what I/O devices you were using. We called this device independence. If you were going to be reading records from a device, you did not want to know in your code that it was a card reader you were reading from, or a tape drive that you were reading from, or a disk file that you were reading from. So we invented this concept of device independence. And here we are, and I'm looking at that Rails app and thinking the device is dominating everything about this code, down to the directory structure. The device dominates everything. This is wrong. This is fundamentally wrong. So I started thinking about architecture. What should the architecture of an application look like? And I took a little side trip down to the architecture of buildings. What does the architecture of a building look like? And I brought up a few blueprints, and well, you can look at this one. You can tell it's a library, right? The shape of the building tells you it's a library. Ignore the title. It's a library, and if that one doesn't convince you, that's a church. The shape of the structure screams out its intent. It tells you what it's intended for. You look at that and think, my God, that's a church. Either that or it's a very strangely constructed theater. But that is some place where a whole bunch of people are going to sit and listen to some guy pontificate on stage. Yeah. The shape, the architecture of the building screams its intent. Where was the intent in that directory structure? And I didn't see it. And it occurred to me, architecture is about intent. The architecture of a system is not about the frameworks that the system uses. It is about the intent of the system. What I should have seen when I looked at that directory structure is a list of the intent. All the use cases. I should have seen all the use cases of that system. One in each directory. I should have seen, add whatever it was. I don't even know what that system was. All I knew is that it was a Rails app. So here's the guy. This is Ivar Jakobsen. And Ivar Jakobsen wrote this book that I told you we all lined up for in 1995 to get a copy of. And the name of this book was Object-Oriented Software Engineering. Does anybody remember when object-oriented was a really important word? Right? And nobody knew what it meant. Nobody knows what it means now. But it was very important in those days. Right? And we all wanted to know object-oriented design and object engineering and object-oriented analysis and stuff like that. He wrote this book, and I want you to look at the subtitle down there. A use case-driven approach. Does anybody out there remember use cases? Remember the use case furor that went through the industry in the late 90s? We all had to know about use cases, and all the consultants jumped on board that, and they all had to outdo each other. So each consultant published a PDF. Well, there weren't PDFs in those days, so it was probably some kind of God, what was the name of that printing protocol that we all used, that laser printers all used? What was that? A PostScript. What language is PostScript? What's it based on? Forth. Any Forth programmers out there? Anybody done any Forth programming? Oh, somebody has. So if you want to have a lovely geek out weekend, right? Get rid of your family, tell them to go away because you're going to go down a geeky rat hole. Fire up a Forth engine and learn a little bit of Forth. It will twist your brain in a strange way. And you will come out of it with a great appreciation for PHP. So Jakobsen, he writes this book. He says, look, architecture is about the use cases. It's about what the system is supposed to be used for, the intent of the system. And he gives us some examples of use cases, which I've got here for you. This is an example of a use case, simple idea. In this case, it's a use case for an order entry system. And this order entry system has a use case called create order. And you can see that it lists the incoming data. It doesn't give you any real detail about the incoming data. It just sort of says, there's a customer ID coming in. I don't know, what it is. Might be an integer, might be a name. I don't know. I don't care at this point. And it's got some shipment destination. God knows what that is, but it ought to be in there. And payment information, customer contact, shipment mechanism, all this stuff. No definition, no detail. The whole purpose of a use case is to avoid detail. Because detail is the stuff that happens later. And then there's the course of events. And the events are very simple. The order clerk issues the create order command. That's not even part of the use case. That comes before the use case. And then the system validates all the data. It doesn't tell you how. It just validates it somehow. System creates the order and determines the order ID. That's probably a database function, but I don't bother to say that here because I don't want to mention the word database in here. And then, by the way, databases. Does anybody get that feeling that databases are the center of the system? That the programs are the little minions that bow before the great God database in the sky? That all significant things actually happen in the database? The database and the data model are the king. What is a database? It's an I/O device. We're not supposed to know they exist. Databases are places where you put bits. We don't want them to be the great God King that we surround our code around and bow to it. The database is a detail. So I don't mention the word database here, that's fine. And then in the end it says the system delivers the order ID to the clerk, probably over a web page or something like that, but I'm not going to say anything like that. This is a standard kind of use case. Now what Jakobson said is that, okay, you've got these use cases, you can turn them into objects in an object-oriented sense, right? He was writing this book called Object-Oriented Software Engineering. So he said you can turn every use case into an object, which he called a control object. I've changed the name here. I've called it an interactor object. People have yelled at me for this and said, Bob, you should have called it a use case object. There's a certain amount of sense to this, but I stick with the word interactor. The interactor object knows the application-specific business rule. Now, there's two kinds of business rules. There's the application-specific business rules and the application-independent business rules. What is the difference between the two? Well, application-independent business rules are always true. Even if you didn't automate the system, they would be true. For example, the interest charge on an account at a bank. That is an application-independent business rule because the business rule is true even if you don't automate anything. What is an application-specific business rule? That's a business rule that is specifically related to the automation, to the application itself. Use cases are cases of the way the application is used. So they are application-specific. They are somehow dirtier than application-independent business rules, but they are still business rules. Where do we put the application-independent business rules? Well, Jakobson had an answer for that. He said, we're going to put those in things called entities. Now, lots of people nowadays use business objects, right? We all have business objects, and business objects are a kind of hybrid of these two concepts. And actually, most systems don't make any kind of distinction between business objects and UI and databases, so they're just kind of messes. So here we are separating the application-independent business rules, the entities, from the application-specific business rules, the interactors. And it is the job of the interactor to control the dance of the entities. The interactor will be given a task, and the interactor will then control the dance of the entities, telling the entities to do their little jobs, and then gathering information from those entities to present back to the user. And for that last function, Jakobson had boundary objects, which you can see here. I've drawn them here in UML as kind of interface objects. And every interactor typically has two such boundaries. One, which it derives from, so this little arrow, this funny little pizza wedge, that's the derives from arrow, or the implements arrow. That would be the input boundary. Data would come into the interactor through the input boundary. And the other one, the one that has the open arrowhead that's going outward, that is the output boundary. So the interactor gets its data through the input boundary, controls the dance of the entities, gathers information, and sends them out the output boundary. This was Jakobson's architecture. And it is a lovely architecture. It separates things very nicely. You now have a whole bunch of use case objects, and those use case objects talk to a whole bunch of business entity objects, and then you have boundary objects that control the flow of information in and out. Very nice. Now let's just walk through the whole process here. We've got some delivery mechanism out there. It might be the web. Might be a web page or a web system out there. I don't care. Might not be. Might be a console-based system. Might be a thick client-based system. I don't really care. Something is going to be providing input to me and accepting my output. And there's some user, and that user sits down there, and eventually the user is typing in information which our system doesn't even know about yet. And then at some point the user pushes some button or hits some key that causes the entered information to go into the system. So the delivery mechanism, whatever it is, packages up all of that information that the user typed in and then passes it through the boundary, the input boundary, into the interactor. I think I can actually show that here. I think I've got a little kind of quasi-animation. There it is. And notice that the delivery mechanism has created something that I call a request model. A request model is a plain old object, a data structure, if you will. It does not derive from anything. It is not part of any framework. It doesn't know anything about whether you're using a God knows what framework or God knows what engine or anything else. It's just a bunch of little data objects that have been translated from the user's input into a nice convenient form and passed into the input boundary so the interactor can get at it. And then the interactor grabs that and uses that request model, parses it, understands it, uses it to control the dance of the entities. So now the entities are busy doing their thing, and the interactor is controlling them, making sure they do the right stuff. And then the flow reverses, and the interactor gathers the result data from the entities and collates it and manipulates it and does whatever it needs to create yet another data structure called a result model. And that result model, I think you probably have anticipated this already, goes through the output boundary to the delivery mechanism, which formats it for the user and sends it on its way. A very nice, cogent little architecture. An architecture that would allow us to create business objects named for the use cases of the system. If I were to see that in a directory structure, I would know what the system does. Now, let's say that we're using a framework. Some wonderful web framework that does lots of interesting work for you. Where is that framework here? Answer? It's not anywhere here. Why would it be? Because the framework is an I/O device or a manager of I/O devices. The framework is a detail. Framework's not part of the application. The framework's just a bunch of tools that you use to help you do this. The framework must not sit at the center of everything. The framework must not be the thing yelling out to everyone, I am a Rails application. The framework should be hidden away in a small corner. And you use it as you need to use it from time to time. What about Model View Controller? Aren't we all supposed to be MVCing here? Who invented Model View Controller? Does anybody know who invented this? Where it came from? Say it louder. Smalltalk, yes, it was in the language Smalltalk that it was created. It was created in the 1970s by this guy. And I'm going to butcher his name because no American can say his name. It's Danish. It's Trygve Renskaug. Completely butchered his name. He wouldn't say it that way, but it's the only way I can say it. And in the 1970s, he invented this lovely little idea of Model View Controller. I met Trygve. I was in Norway. This was 8 years ago now, I think. And we were both in the speaker lounge of a conference. And I walked in, and I was looking for a place to plug my laptop in. And this grizzled old guy walks up to me and hands me a power strip. And I don't even look at him, right? Oh, thanks a bunch. And, my fingers brushed him, and I looked up. So it's Trygve Renskaug. I haven't washed that hand. The idea behind Model View Controller was lovely. Now, by the way, it was for Smalltalk, right? So it was small. The idea behind Model View Controller was a small idea, not a big idea. This was not a sweeping architecture to conquer the masses. This was a little thing. And the way it worked was this. You would have a model object. A model object understood simple business rules. Let's say we're doing a digital representation of the time on the screen, a digital clock on the screen. Well, the model would understand time. It would understand how minutes and seconds are related and how hours are related to them and might understand calendars and things like that. It would have no idea whatever how this data was displayed or how input came in. The controller was a little object that watched for input, typically with the mouse. So the controller would watch the mouse and the keyboard. Then it would capture mouse events and keyboard events, and then use those to send commands to the model to change the time. The view, and I've drawn that with that thick arrow because the thick arrow is an observer relationship. It's a callback relationship. The view would register with the model, and whenever the model changed for every reason, the view would say, hey, or the model would say, hey, view, I've changed, and then the view would pull data out of the model and display it for everybody. That was model view controller. Real simple idea, and if you look at it carefully, you'll see it's input, process, output. When we wrote these kinds of things in Smalltalk, we wrote them for small things. A radio button would have a model view controller triplet. A text box would have a model view controller triplet. They were little things. They were not the grand scheme that it has evolved into now. Nowadays, model view controller looks something like this. Now, there's some relationship here, but it's very different, right? You've got the web out here, and God knows what that is. It's some horrible framework in the sky that everybody uses and no one understands. And then you've got a bunch of controllers that the web calls, because the web parses the URLs and figures out what to do, and calls the controllers with the data. And then the controllers reach over here and talk to a whole bunch of business objects, and then the controller hands control over to the views, and the views talk to the business objects and then hand that data back to the web. And that's the model view controller that we all know and love today. And one of the problems with this is that there's no clear separation of where you put input processing and output processing. So controller-like stuff manages to work its way into the business objects. And view-like stuff manages to work its way into the business objects. You don't have a really good separation. So I like to avoid that by separating out the use cases into interactors and boundaries and so on. So this is kind of the picture that I like. You've got a bunch of entities out here, which are sort of like your business objects. Interactors are the things that isolate you from the outside world and control the dance. You've got an interactor, which in this case has created a response model. It's going to pump that out the boundary across that double black line. When I draw double black lines, that's an architectural boundary. There's something significant about that particular boundary there. Notice that all the arrows point the same direction across that boundary. Architectural boundaries look this way. Right? All dependencies point inwards across an architectural boundary. And more importantly, they point towards business rules. They point towards high-level concepts. There are low-level concepts on the one side, and all those low-level concepts point towards the business rules. Why? Well, take a look at that left-hand side. And never mind what it is. I'll tell you what it is in a minute. It's a plug-in to the business rules. If I were to take that whole left-hand side and wrap it up into some component and hand it to you, you could plug it into the business rules. Business rules don't know it exists. All the business rules know is, oh, there's some plug-in coming in. Okay, well, I'll use it normally. It's a plug-in to the business rules. Now, what is this thing over to the left? Well, that's the web. The web interface should be a plug-in to your business rules. Your business rules shouldn't know that the web exists. Shouldn't be related to the web at all. And the web should plug in. And you should be able to unplug it and plug in something else. You should be able to plug in a console interface. And you should be able to unplug that and plug in a thick client interface. Or what is that horrible architecture that people used for so long? Service-oriented, that's what it was. Okay, so you should be able to plug in a service-oriented interface. And none of the business rules should care at all, because the device is independent. We want independence from our devices. Now, take a look at the left. The left is kind of interesting, the way I've drawn it here. I've got a response model that's going through the output boundary to a thing called the presenter. What the presenter understands is the format of the data that the web will eventually use. It does not know that there is a web, but it does know the presentation format. So the job of the presenter is to create a whole bunch of strings. If you have a date, for example, make sure there's a date in that response model, well, we're going to turn it into a string. The presenter will turn it into a string and store it in the view model. If you have currency in the response model out there, the presenter will turn that into a string. If you have a button, and that button has a name, the presenter will create the name of the button and store it in a string somewhere so that everything that needs to be displayed on the screen winds up in this data structure, the view model, which is just a normal old data structure again, a bunch of strings in it. And then the view, which you see there drawn ghostly, is just a stupid little program that pumps data out of the view model and puts it on the screen somehow. Who's doing TDD? Test-driven development. Who's doing this? Hey, we got some people applauding. That's good. We got people with their hands in the air. That's good. About 10% of you, I would say. Okay, this is about, well, if I were to do this at a Java conference, I would get a third. If I were doing it at a Ruby conference, I would get half. Right? So it gives you an idea of the demography here. What the hell are the rest of you doing? You're not doing test-driven development. What the heck are the rest of you doing? How do you control your code if you are not writing tests? And if you are not writing tests with some kind of discipline? Are you writing the code and then just kind of looking at it on the screen and saying, oh, geez, it looks like it works? Is that what you're doing? Is this what our society needs? Now think about this very carefully, because our society is coming to a point where it's going to start saying, you know, these software guys, we depend on them for everything, and these guys can't do a damn thing right. Right? Who remembers October 1st, 2013, the date that the Affordable Care Act website was supposed to come online? And it did. It came online, didn't it? Can you imagine the programmers, right? They're going to turn it on. They really shouldn't turn it on. And we tried to tell them that they shouldn't turn it on, but they're going to turn it on anyway. Because of that fiasco, and it's very interesting, right? Here's a law passed by Congress, signed by the president, which dictates that a software system must be ready by a date certain. Now, never mind the stupidity of that. Someone who wrote that law had no understanding of how software systems work. Never mind that. They turned it on. And it almost derailed that law. That law almost went down because the software developers could not manage to communicate well enough to their managers that they shouldn't turn the damn thing on. This is the problem that you and I have. You and I are programmers, right? And most of the time we don't think about society or people. Because, we're like, this is cool. And we don't quite get the fact that our entire society is depending on us for the next day's operation, for society even functioning. So you can imagine what's going to happen one day, because here's what's going to... Does anybody know what happened at Night Capital? Anybody heard the story of Night Capital? Night Capital, this is about 8 years ago, 9 years ago. Bunch of guys, right, they're writing this trading system. They do high-frequency trading. And they figured out a way to take large trades and break them up into small trades. It's a trick that trading companies use to hide the fact that somebody made a large trade. They break it up into small trades, and they pump it out over a bunch of different networks. And they had a lovely algorithm for it. It worked fine. And then they decided to rewrite the algorithm, so they put a whole new different algorithm in, but they left the old algorithm in. They just disabled it with a flag. Now, already there should be sphincter muscles tightening in the room. It's like, they did what? They left all that code in there and they just disabled it with a flag. And where was the flag, you say? In the incoming transactions. Ooh. But as time went on, as things do in software, this all just got buried and hidden, and no one knew that it was a problem or even there. And then one day there was a new tax law that came along, and certain transactions had to be flagged as being a part of that tax law, and they saw this extra little bit sitting there and thought, oh, we could use that. And they wrote the system properly, and they went in at night and they installed it into all the servers. Well, not all of them. They forgot one. They forgot one. They had 14 servers. They forgot one. They put it in 13. Just didn't quite pull the trigger on the 14th. Somebody miscounted. And they tested it, and it worked just fine. They turned it on, and they got a call within about 10 minutes from the SEC saying, hey, something weird's going on, like you're making crazy trades. And the programmers panicked and said, oh, man, there's something wrong with the new code. So they pulled all the new code out and put the old code in to all the other servers. $450 million in 45 minutes down the tubes. The CEO woke up in the morning without a company. The vultures had already swooped in and bought it out from underneath him. This is the kind of strange thing that you and I might find ourselves involved with. Now, what is going to happen, right? And it's very predictable, right? Some poor software guy, maybe you even know him or her, is going to do something stupid and kill 10,000 people. And it's just going to happen. You know it's going to happen. It's not that hard to think of the scenarios. And then what? And then what? The politicians of the world will rise up in righteous indignation, as they should, and they will point their fingers right at us. Oh, they'll try to point it at the CEO, but the CEO said, the software guys did it for whatever reason. And that finger will come right to us, and they will ask us the question, how could you have let this happen? And we'd better have an answer for them. Because if our answer is, well, you know, the boss said that it had to be delivered on Tuesday. If that's the answer we deliver, then the politicians of the world will do the only thing they can do, the thing that the public will demand that they do. They will pass laws. And you and I will all become public servants. They will tell us what languages we can use and what processes we have to use and what signatures we have to get and what books we have to read and what courses we have to pass, what degrees we have to have. And you and I will become regulated. And that's something I would like to avoid. Now, other industries have managed to avoid this. How did they avoid it? Doctors. Doctors avoided this by coming up with the regulations on their own, before the government could ever get to them. And then finally government said, you know, these doctors, we've got to regulate those. And the doctor said, well, it just so happens that we have some. Would you like to use ours? And government is essentially lazy. Right? Said, hey, the doctors have already done it, like, so we could claim credit for it. This is what you and I have to do. We have to come up with the regulations before the government comes up with them. We have to enforce them. We have to obey them. And the first step in doing that is to identify what these regulations are and doing them ourselves without anybody else. And test-driven development is a decent candidate for such a regulation. It is a lovely little discipline that everybody can follow. It's not that difficult, doesn't take any extra time, it makes things go fast, gives you a lot of control over your code. Let me tell you, you should think about this very carefully. So, I want to test that interactor. I want to write unit tests that test that interactor. Can I? Well, yeah. I just load up a fake request model, pass it into the interactor, look at the response model, it comes out, look at the data in there, says, yep, that's right. I can write tests for that interactor with all the entities in it, and I don't have to have the web running. The web server doesn't have to be running when I do that. I can just make calls directly into the interactor, passing in data structures. Or, can I test that presenter? Can I test the way that works? Yeah, it's easy. I'm going to pass in a fake response model, pass that through the presenter, and look at the view model. Do I have to have the web running in order to do that? No. Because I don't need the framework in there. I don't need the web in there. I can test all that stuff in isolation. Being able to test in isolation is a decent indication of a good architecture. Being unable to test in isolation is a decent indication of a crummy architecture. If you must fire up the web in order to test your app, something is wrong. What about the database? I mentioned this before, right? Is the database the great God in the middle of your systems? Now, you know what happens when you've got a great God in the middle of your systems? It also becomes the dumping ground. Oh God, where do we put this function? Put it in the database. It'll go in there somewhere. I want you to think of databases as not existing, right? When you're designing applications, I want you to think about the function of the application, not the data of the application. I want you to write the code that does the data manipulations and ignores the data storage. Defer the idea of data storage to a later time. Let me show you an instance of that. Yep, there we go. Long, long ago, about 2000, my son and I wrote an application called Fitness. Has anybody used Fitness out there? You see anybody who's used Fitness out there? I don't see any hands up. Okay, all right. Fitness is a wiki. It's also a testing product. You can write acceptance level tests on wiki pages. I'm not going to get into the mechanism there. What I want to talk about is the architecture. We knew we had to write a wiki, and so we said, well, all right, wikis, you have to store pages. We're going to need a database. We want this to be open source. The year is 2000. What open source database was there? Well, there was MySQL. All right, let's get MySQL and fire it up, and we'll use that. And somebody said, well, we don't have to do that yet because there's all this translation from wiki text to HTML. Why don't we do that first? We said, yeah, that's a good idea. So we're doing test-driven development and writing tests, you know, to make a little test pass, and next test make it pass, and take this wiki text and translate it into HTML. And it took us 3 months. 3 months of working, parsing all of the HTML, or parsing all of the wiki text, turning it into HTML. And about 3 months later, we're all done with that, and we've got a functioning translator. We can't put a page up on the screen, but we've got a functioning translator, and all the tests are passing, so we think that's pretty good. Then we say, okay, now we need to get the database so that we can store this and put it up on the screen. And somebody said, well, you don't actually need to have a database for this because what you could do is take the data and put it into a hash table in memory. Now, a hash table in memory is kind of like a database. It's just that it's not out on disk. And so here's what we did. We created a little object called wiki page, and it had the little translate function in it to HTML. That's the code that translated from wiki text to HTML. And then we also put a save function in there to save it in the database, but we didn't let it save it on the database because we made a derivative of this called in-memory page. And that just stuck it into a hash table. Okay, now we could write more code. And we wrote all the code that linked pages together and put them up on the screen and actually ran tests and everything. It took us a year. We worked a year this way. And we had the whole thing working. Couldn't save anything. It was very inconvenient. But it worked, except that you couldn't save anything. And then we finally said, okay, well, it's time to get the database. Let's go get MySQL, and we'll put it in MySQL. Michael Feathers was there at the time, and Michael Feathers said, you know, you don't actually have to do that yet because it'd be really easy to take that hash table and write it out to a file. And, you know, you're not going to live with it that way because who the heck wants to live with a flat file? But for the time being, you could do that and keep on writing tests. And we thought, well, that's a good idea. And he actually came back a day later with the whole thing working in a file system mode. So we just kept on working. And now we had persistence, and we could save the pages. And we took it on the road, and we showed it to customers and clients. And lots of people liked it. And we kept on adding new features to it, on and on and on. About 3 months later, we came to a very interesting decision. We don't need that database. We never put it in there. There was no point. We had it all functioning. It works great. We pushed that decision right off the edge of the project. Now, normally you would think that the choice of database is a fundamental architectural decision. It's not. We pushed it right off the end. We took it and pulled it off the planet. Except for one little thing. About a year later, a customer of ours said, we got to have everything in the database. And we said, well, why? Some database vendor came and told our bosses about data assets. And now they want everything in a database. And we said, well, it's a great word, isn't it, data asset? Don't you wish you came up with that? Don't you wish you were the marketing guy at Oracle who came up with the idea of data asset? What a great way to talk to financial people. Do you have, you've got data assets? No, I didn't know you had data assets. Oh, yes, you do. And you need our system to help safeguard your data assets. Wonderful idea. Anyway, here's this guy. He comes to us, I got to have it in a database. Why? Oh, it's a data asset. I got to. So we showed him this structure, right? We said, look, just make another derivative, call it your database page, and all the controls are there. It's all going to work just fine. He came back a couple of days later. The whole thing was working in MySQL, for God's sake. They crammed the database in at the very last minute. We used to ship that as a plug-in to Fitness for several years, but nobody used it, so we threw it away. Even he threw it away in the end. He said, it was useless. No point in doing that. There's an interesting lesson to learn from that. A good architecture allows major decisions to be deferred. Deferred to a time when you have more information. A good architecture opens up options, does not close them down. It opens options. It allows you to experiment with lots of little details without committing to any of them. A good architecture maximizes the number of decisions not made. Think about that very carefully. It happens to me frequently enough that I ask people, what's the architecture of your system? And they'll say something like, it's a Java system, we're using Spring and Oracle. And that is not an architecture. You have not given me an architecture. What you've done is showed me all the tools in your toolkit. You haven't described the architecture to me. The architecture should make the choice of tools irrelevant. And what that means, of course, is that we want all of the peripheral stuff, like the database and the frameworks and the user interface, all to be written as plugins to the use cases, so that you can unplug them and plug them in later. You don't like Oracle? Plug in some other database. Right? Maybe you want SQL Server. God help you, but all right. Maybe you want to do that. Yeah? Or maybe you'd like to experiment with some NoSQL databases. You can plug it in, because the application doesn't care. Oh, I already talked about that. I could talk about it some more, though. See? Yep, good. That is the end of my discussion. I can't see a thing out there. The lights have come up. Are there any questions? I don't know if I've gone over my time limit or not. My watch died.